In the next example, I ask you to use isoclines and graph the slope field for this differential equation. For this differential equation, rate of change is equal to y minus t. What are we going to do? We're going to take y minus t and set it equals to some constants like c, because it gives us the rate of change and we can easily analyze the rate of change. So take a look. If I plug in 0 for c, y minus t becomes 0. What's the meaning of that? It means that y and t are the same thing, or y is equal to t, right? Very good. You get a set of line segments with slope equal to 0. When you set c equal to 0, it means that you are setting the differential equation, the rate of change, equal to 0. When the rate of change is equal to 0, you basically have some horizontal lines, flat lines, but in this case, you're going to have flat line segments because you look at this locally. Suppose we plug in c equals to 1. What's the meaning of that? It means that the slope of the lines or the rate of change are equal to 1. So you take your differential equation, y minus t, and you set it equals to 1. Or y is equal to t plus 1. Take a look. Now, locally at each point, you have slope equals to 1. These line segments are just showing that you have increasing line segments. Suppose c is equal to 2. What's the meaning of that? It means that the slope is equal to 2. It's going to get a little bit more steep. Or y minus t becomes 2. Or y is equal to t plus 2. Take a look. You're shifting these just 2 units. Now, if you plug in -1, it means that the rate of change is going to be negative. You're going to get decreasing lines, decreasing line segments. So when c is equal to -1, you get decreasing line segments, and these are all locally behave like this. That's why you don't see a continuous line. You just see a bunch of line segments. When c is equal to 0, you have a bunch of flat lines, and when c is equal to 1, they are increasing line segments, and when c is equal to 2, it means that the slope is equal to 2. So we expect the lines to be a little bit more steep. And finally, if you use a graphing calculator or graphing website, you can see the behavior of the solution or the family of solution for this differential equation.